Hello and welcome to my 45 filters of image processing. I'll try to do it as quick as I can since we have a lot of filters to go through, but I'm gonna cut for each filter when I explain it, so it's gonna go a bit faster, I hope. So let's have a just have a quite glimpse on all the images I made, and I also made it like this, so some of them are more laggy than others because they're more like pictures shown at the same time on videos. So yeah, this is one of them where you see like original image, grayscale, black and white, some erosion, dilation, opening, closing, some edge detection, edge detection, some color detection, and here we have, this is a bit laggy, but then we have the mean filters, the Gaussian filters, the glamour glow, the pre-lit, the dissolve. We're gonna see them later, of course. Normalized, RGB, invert, alpha, solid pepper noise, brightness, contrast, auto contrast, gamma, exponential, and logarithmic. ACAS, HVSV, hue shift, sepia, saturation, pastel, and edge detection, vertical, max, median, minimum, blur, EBUS, block analysis, and pixelation, resize, crop, and pointer sizing. And then there's going to be some more in this one because we have to like also look at the squares. They're also part of the filters. So let's take it from here. The first thing is we need to show that we make an unsigned char called pixels, which is assigned to the vid grabber pixels, a built-in function that grabs whatever is inside the video, inside the input from the camera, and then points at it, so we can use it for later use in our other video filters. And then also quick in our header we have basically the vid grabber, which is a built-in function, and also we have some unsigned chars, so we use to point at our picture of our texture. So we need to have some allocated space for our pictures, videos, in order to show them, and then we have an off texture in order to show them, which where we allocate some space. Later on we load data, loads the data inside the video texture, and then we draw it on the frameworks. And that's basically what we do with all the video filters. And later on we're gonna go, there's a lot. And we're gonna make some HSB, where we're gonna look at the hue, saturation, brightness, and the cam width, cam height, which we use in order to get how many on-site chars we're gonna use, how many pixels the video has, and then some kernels we're gonna use in order to change some pictures. We're gonna look into that, and then there's some different variables in order to make our block analysis successful. So let's just take a better look at what's more interesting. Let's have a first look. Should be the grayscale. When we allocate space for a picture with a picture with colors, we have like 3 dimensions, like red, green, and blue colors. So we have to also allocate 3 times as many a value 3 times many the pixel there is. I hope you get that. But as you see here, we have an output grayscale, which is a video texture which should be assigned to the pixels. This is the first color of the pixel, plus the pixel. Second color is like which column should like this just takes a pixel in the picture, which is controlled by the for loops, and it's just like which column have we already been looking at, times what column are we at now, plus x, where are we in the x system. So it goes something like, can I point, okay, like x, 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 and then it goes, y goes down, so we have like chem width is 1 now, or times with 1, and then we go back, and then, okay, I hope you also get that. They're very basic. And then we have like 3 times, it's done 3 times for each pixel in order to get 3 colors, and the first color is found as 0. The first, and then the next is the next position in this array of a picture is 1 with green. It must be green, and then plus with the next one, which is blue. And then in order to get a grayscale, we simply just divide these colors so they get the same amount, the same color, meaning it's gonna be gray, or same value, so it's gonna be gray. So we divide it by 3, and then we get a grayscale, which we're going to use later on. We could also just avoid having like a, actually I think some places we did that. Well, we did it down here, like when we use luminance instead of red, green and blue, we just need to have like a cam width and cam height, because we don't have any colors in it. So that's an easier way just to use grayscale. Then we should just remember not to allocate too much space. But okay, that was the first grayscale. Now we're like into it. Now we're gonna go like a bit quicker at the more exciting tempo, I guess. I hope. Next picture filter I want to show you is just a black and white picture, and then we go to dilate and stuff like that related to black and white. And as you see down here, I am only in total black and total white. And the way we do that is that we make a threshold. I'm gonna find that. And here it is. Also, it's known as binary filter, because it's only like values 0 and 20, 255. Like it only has 2 options, like white or black. So let's take a look at that. That's simply just having like this pivot point saying 127 as the pivot point. If it's brighter than that, it's going to be total bright 255. If it's lower, it's going to be 0, and that's basically it. Next filter. The next filter will be dilation and erosion. And as you see, what it does, it puts a kernel around 1 pixel and sees if there's only like 1 pixel of something, it's gonna okay, let's take it instead. But it's gonna look like this. It's gonna either what do you say, like dilate, like we say, dilate the white colors, and this is gonna dilate or remove the white colors. And as we see here, it's done by this. We use like this kernel, which we put on top of it, like having 9 pixels or 8 pixels on 1 pixel to see how many white pixels there are, for example, are. And that's what we're gonna do. I guess we're gonna do it here. We're gonna see if the sum, we're gonna take each pixel divided by 255. So if it's a black picture, it's gonna stay 0. If it's a white picture, it's gonna be 1. So the sum can therefore be max 9, and if it's a kernel, for 3.3, max 9, and minimum 0. Yeah, and then we're gonna state if the sum is bigger than amount of SE squares, that's so 9 in the 3 multiplied with 3 case, it's gonna be white. So this is erosion. So if there's a lot of only if there's a lot of white spots, it's gonna print out the 1 pixel white. If on the other hand the erode pixel is not equal to 9, if not all pixels should be white, it's gonna be black 0. And it's the opposite with dilation. Okay, dilation is not here, but it's the opposite with dilation. Then this is just 1 instead of 9. Okay, that's basically how you do dilate and erode. Okay, and when you have dilate and erosion, you can go in and see it opening and closing, because that's just what they just use closing, dilate and erosion differently. If we take the opening, let's see the code. As you see, first we're gonna take the opening, and then we're gonna have, okay, the sum should be, we're gonna use the picture of erode, meaning that we have already made an erosion, and then afterwards we're gonna dilate it, meaning that if the erosion, if the pixels, if we put a kernel on top of the erosion picture, and then see if there should be any kernels where there are only one white picture, then, or not only one, more than just one. On the other, with erosion it's more than just 9, that's max. Okay, and then if it's more than just one on each one, it's gonna be white, therefore it's gonna dilate, and therefore it's gonna look like something like this. First it's gonna erode, and then it's gonna dilate, and it's just the opposite with closing. Yeah, and then you see we get a lot of noise. We get rid of a lot of noise, and you see there's nothing like my hair should look at something like this. That's how it works. Next filter is boundary detection, where we see like the boundaries, like we do in this. It's this picture down here, and as you see, you can see the palms. They have like nice boundary wide kernels, or at least big pixels. And then let's see the code. It's just this one. What you simply do is that you have this by this video texture output. You take the black and white picture and minus it with the output erode in order. So you get like, you have a picture black and white, and then you take and erode it, so it's gonna be like, you can't really, the edges are gonna be like, if you have a ball, it's gonna be smaller because the edges are gonna be smaller because you're gonna erode it. If you have a black ball, of course. So therefore, when we delete it, we're gonna delete it, so we're only gonna see that like that disappearing outline. Yeah, that's basically it. Let's go to the next filter. The next filter is gonna be Grassfire. Grassfire we use in order to get our blob analysis. Find some blobs in our picture. Like you can see all the white over here is like one blob because it's not separated by any black pixels. And let's see how we do that, how we make a Grassfire. The first thing we do in our code is that we take our Grassfire video texture, which we can output, and put it as an output opening. So we're going to use the opening thing we have from the morphology videos from before. And then also we're going to take the output Grassfire and put it equal to a label array, which just contains some numbers which we're going to label each pixel which is inside a blob. So the first blob have pixels labeled with number 1, for example. And that's how we do it. We're going to look at it now. We're going to have it down here in like we're going to run through the whole we're going to run through the picture by having double for loop, and then we're going to see if a label inside this array is equal to 255, meaning it's a white pixel. Then we're going to take the Grassfire and it's going to run. So it's going to run from first it's going to run to the right. Oh, okay, fuck that. It's going to run a function, and let's look at that function. The function you see here, and what the function actually does is that it's a recursive function. So it has some values up here, which is like the y, x coordinates, and then the label counter, meaning what label you're going to use. And first when you find the first label, the first pixel in the blob, you're going to label it with the first label count, of course. And then you're going to see, okay, I'm going now. The Grassfire. What it does is that it's gonna look if you're gonna have an if sentence at first, which states that it's gonna see if the pixel right to the right of the initial pixel we add is inside the camera width -1 because we don't want any borders interfering, outside borders interfering, and also that the label array to the right, you see here like to the right is done by the x plus 1 is 255. If it is that, it's gonna run the Grassfire again, going backwards. Now with the label count. With x plus 1. So it's gonna start from the next point. So starting here, looking there, 250. Yeah, starting here, going there, 250. And then when it doesn't, because it's not true, it's gonna go down instead. It's gonna go y down. So it's gonna whoop whoop, go down, see if that's 255. And it's inside the cam height border thing. It's gonna do Grassfire again if there's 1. And then it's gonna go down. If there's no 1, it's gonna go left. If there's no 1, it's gonna go up. If there's no 1, until there's no more left. So it's burned all the grass, the whole blob is found. And then it's gonna recursively go all the way back again. So it's gonna go like back. It's gonna wind up at the first spot once again. And then we labeled them all with the label count. And then we can use that in order to make our blob analysis. And that's basically how we start the blob analysis, the Grassfire. And then there's some more filters inside this Grassfire we can do. Or not inside, we can just play around with this blob analysis, which we're going to do now. And then I just need one more thing about the Grassfire, is that the amount of blobs we're going to find, which we're going to use later on, is assigned to just the label count, so we see how many blobs there are. And then we have a label count, so each time it's run, it's gonna, when it has found label, the first blob is gonna go to the next one. And then down sorry about that, down here we're gonna see that the blob number 1 is gonna have a gray tone, a gray color instead of black or white. And as you see, we have it right here. It's gonna be black, this one. Yay! Let's take a look at area. So the Grassfire function we made is got the Grassfire label array, which I call it, is an array where we put in the count. It's actually a way to present the image of the Grassfire itself, or also just by changing the labels, having label values on the places in the array where there's white pixels, the white blobs. I hope you understand what I mean. Because then we do this in order to find the array. We make a vector in order to store some values like an array. We run through the whole picture and finding if we found, for example, the first thing we want to find is like, first time we want this function is the time for the first blob. So which is 1, label 1. So if the label is 1 on a pixel, it's gonna plus area by 1. So we found the area. So it finds all the pixels with the value 1 and passes to area. And then we take a blob vector push back function, so we push it inside an array. So we have and also we have amount of blobs it's going to run for each, so as many blobs there are, and we can find that by having the blobs up here. We know how many blobs there are, and then it's going to push in there. So we're going to have an array with different areas from different blobs, and then we're going to, if you see here, we're going to try the first one, the gray one, and as we see it, we can just see that gray blob area. It's gonna be smaller when I do like this. See? Small gray area. Really? Oh, well now it's big because it's over here. So that's basically it. Let's go to the next one. What the bounding box simply does is that it draws a square around the Oh, fuck. Oh, sorry, that's not the bounding box. It is up here. It draws a square around the smallest x and the widest x and the smallest y and the highest y. And then you see we just make some if sentence saying if the label is equal to 1, yeah, and then if x is the smallest, then minimum should be or smaller than minimum, which is initially assigned to the biggest number in the whole picture, and then it's going to be assigned to the minimum value, and then we can use the minimum value in order to draw our square off rect, and we're going to have no fill in it, and it's going to be off rect starting from camera width, just to get it at the right position where the picture is. Going to start from minimum x and minimum y, and stretch over minimum max minus minimum y x, sorry. So it's going to stretch and make a square all around, and we just make one because the function is going to run so quickly and you're not going to notice very much. And as you see here, boom, boom, there are some squares around our blobs. Yeah. The next thing we want to find out, as you already seen maybe, that some boxes are red and some are blue, and I just made it so we're gonna make a bounding box ratio, which just finds out whether the square is wider than more wide than it's high. Yeah, and that's we simply do by saying minimum max minus minimum y should be divided by the length. Y divided by length is, if it's smaller than 1, it's gonna be blue, and if it's bigger than 1, it's gonna be red. And as you see, it works down here. So next filter. Next filter, not filter. It's not for filter. It's just something we play with blob analysis. It's called compactness, and it's gonna look how compact the. We can see up here how compact. Why can't I do that? Sorry, like this. How compact the picture is. So you see, some of them are close to 1. If they're close to 1, meaning that they're almost like if there was a square, it was going to be like square divided by a square. It's going to be 1. But if it's like not a square, it's like something like this down up here. Then you see it's not very compact since there are some black spots inside the square. And that's just the ratio it measures. And sometimes it does it really weird. But I think it works to some extent. The next thing to be looking at is the center of mass. Center of mass is just a place on a kernel on a blob where you should put your finger if you want to hold the balance on it, like the balance spot. And the way we find it is just that we have some mass x and mass y, which we plus equal with the x, so we get like the total x length. Oh, sorry. Total value of all the x's plus together, and then divide by the area of the blob, which is gonna be blob 0.0. Blob of the area. Yeah, it's gonna be blob of the area, and then it's gonna print out the best x balance. As you can see, we can try it out. So it's just gonna be some numbers. Could of course put some spots here, but I just didn't do it. But I know it works, and it was one of the last things we did, so I didn't want to go too much into details with that one. So that's it for the blob analysis. Let's go to the next filtering. Another way of understanding like images is by the RGB. We can use something called HSV or HSB. Actually, I use that better. Stands for hue, saturation, and brightness. And the way we do it is that we're gonna take all the pixels, the red colors, the green colors, the blue colors, put it to a my color red and my color red, my color is a off color built as a built-in function of Open Frameworks. Then you put it there, and then you can get some functions like get hue, get brightness, get saturation in here. And then the my color you can set. This is just actually printing out the exact same picture as we use up here. Or we can just change it easy. And then we can just output each output HSV to the red the red port, red channel to the my color red. So it's just gonna do the same, but we're gonna use it for different things later on. And it's really cool when you, for example, have a color track, because you can have it works as a do I have it anywhere? That would be nice. But you can have it as a cylinder. No, not cylinder. I don't know what it's called. A like pyramid, round pyramid, where you have where it's easier to pick a color and use it for color tracking. Yeah, we're gonna see that later. A way to use the hue is that we have like the hue is not like 3 colors. The hue is just all the colors in 240 color numbers, and then it's gonna show. For example, if we say that the hue can only go from 180, or over 180 it's gonna be 180, and if it's less than 100 it's gonna be 100. So it's gonna be between 100 and 180. And then it's going to look something like this. A little bit more green and blue, but we don't have a lot of red, for example, because red is a different place in this one you see up here. So we only use light from around here. So that's cool, I think. And then we can also change the saturation, which is just a saturation change up here. So if it's bigger than 0, it should be 255, meaning that everyone should be 255, meaning it's going to be like saturated, like this one down here. Yeah, next one. Also with the HSP, we can make like this Savior, or at least we did it this way, where we just go in, make it grayscale, and then times it with the different codes, 112, 66, and 220, at the different colors, well, in the output grayscale, and then afterwards put them inside our output sepia, like put them together in some way, making it output like this brown sepia-ish. Yeah. In order to get pastel colors, we just simply take the saturation and put it a bit down. So it's gonna, this is pastel and this is like the original picture, how I really look. And if you look, it's just dividing it by 255 and then timing it with a bit more. You can also do it differently, but now we did this. And then that's also this one, and then the ACOS. Let's have a look at the ACOS. That's the last one in this window. For the ACOS, we simply take the arc cosine of each pixel, and the way we do it is simply just by taking it, taking it here, and then assigning it to B, and then putting it to B, assigning it to the output. We can do that just putting it into a float, since we only have like one-dimensional arrays. Yeah, and that's basically it. So, oh, and also we can see here, like when you have color challenge, you need to do it like 3 times. A bit random, I say it now, but that's also something you need to do. Yes, let's go to the next window. The normalized RGB we also make is a kind of filter that just shows the red, green, and blue colors inside an image. So even though this is actually green, the pin that I'm holding, but if I do like this, some gray is coming, but it looks like the background, since we only have like that type of color. So it looks more like the background than the actual green color. So, and the code you can see up here. That's how we made it. Just not very interesting. Just divide the picture with with all the pictures together, and then multiply with 255. Then you have it. Next picture. The invert picture down here is actually pretty simple. It's just taking the pictures and inverting them. So as you see up here, each pixel is just 255 is just minus with each pixel. So the actual value, if a pixel has one value, it actually has 254. And if it has a value of 254, the pixel, it's going to have a value of 1. So it's going to change. That's basically it. For the alpha channel, as you see down here, we have like 2 videogrammers just inverted with just flipped, and then the one has a lower alpha than the other one. And the way we do it is up here. Then we have this function here, which just reminds a lot of the one we made with when we had to make a slideshow, where we just times the picture with so we actually change the alpha of it with a number lower than 0.8, and the other one is then 0.2. So they together have a united value of an actual pixel, a alpha one. Okay. And also we can make it a bit different, so it looks really cool. I don't know why. It's gonna look. It's just up here we took like 2 different video unsigned charts. Like 2 video textures or unsigned charts and mix them together into a new one. Down here we take one and then just use one of these on top of it, and then it's gonna look like a more ninja-ish. Now it's gonna look something like this. So fast you can't even see it. Yeah, that's funny. I'm not totally sure why, but it's really cool. It's a really cool thing. Then we made a salt and pepper noise down here, and it's actually also pretty easy to make. It's just having random numbers. We have random number 1 to 10, and if the number is 1, the pixel is gonna print out. No, not if the pixel is not 1 or 2, it's gonna print out. Otherwise, it's gonna be either white or black, and that's basically it. Next filter. Then we have a brightness filter around here, and just basically, I don't want to show the code. It's just basically we just put plus each pixel with a value, with the same value. We plus each pixel with a value, and that's it. And then it gets brighter. And then of course not over 255, because then that's white, and then it's gonna be weird. And then, and if we want to change contrast up, we just multiply it with a value, and then it's gonna be like the brighter parts are gonna be much brighter than the darker parts, which is just gonna be a bit darker or brighter. And then outer contrast is more interesting. Let's look at that code. You see that the light thing are gonna be more light, and the black thing are gonna be more black, like my eyebrows and the wall behind me. What we do with the outer contrast is that we minus 127, so half the pictures, dark pictures, are going to be less than 0. So when we type multiply it with a contrast, it's going to go like both ways. So the midpoints are going to be like about 0. So they're not going to change that much. That's basically it. And then if it goes over 122 plus, it's going to be 255, because otherwise it's going to be too much crazy coverage. Yeah, and that's basically also it. And then if it's not, it's just going to be output with the B plus 127 again afterwards. So it's not going to be like negative colors. Yes, next filter. The next filters are the logarithmic, the exponential, and the gamma. And yeah, the logarithmic, you just take the logarithm of each pixel, and as well you do with the exponential, you just take the exponential of each pixel. And with the gamma, you just put it to the power to a certain number, which in this case is making it more bright. So it's bigger than 1, I guess. Bigger than 2. Let's have a look at those just quickly. The logarithm code looks like this, which states that if the pixel has a value of 0, it's going to be +1, so it's going to be 1 no matter what, and it's going to be 236 over log 236. So log it's going to be 1. No, it's not going to be 1. It's going to be 236 or something like that. But it's going to be bright. It's going to be bright, and then if it's 236, it's going to plus by this one, and then you can actually just remove this part and this part, and then it's going to be 56. So forget what I just said right before, but that's the logarithm of the image. This down here is the exponential image. We'll take the exponential of the image, and then it's going to be like, when it's bright, it's going to be like, I'm going to take my pen down here. It's going to be really bright, like really bright some places, but only where the places where it's really bright at the same time as well. And the gamma is just shown down here. B is, no, that's not the gamma. Is that the gamma? Yeah, it is the gamma, and we just times it with 0.2, meaning it's low, less than 1, and it's going to be brighter. Then we can switch around with it. You can do it like that. And that's the gamma, and let's take the next filter. The next filter will be the pink color tracking filter. And what it does is that we use a HSB, as we talked about before. And then we take a result of that where the hue should be over 210 and less than 230, because that's about the colors pink. And then the saturation should be less than 0 or bigger than 100, and less than 255. So it can be really pink, but not too much little pink, because my hand is, for example, also a little bit pink. So we don't want that. So we actually remain thresholds, and also we need the brightness, so we don't have to have like a certain brightness when we have to do this. It can vary a lot, from 100 to 200, but not 255, because then it's going to be also white colors, not 0 of course, because it's going to be all black. And then this is an if statement, and it's going to be if it's true, this one, it's going to be 255, else it's going to be 0. So if what we see is pink, it's going to come up as white. And then we make a point for it, a track point, which is also a track point. Let me see, track point. I need to track point. It's an off point in open frameworks, so it can make a point inside our picture, to point where, and then we find making a track.x plus x, finding all the x's and plussing them, and doing the same with the y's, and having an n all the times we do it, we can divide it and find the average of the x's and the average of the y's, and then we can find the average of the pink. So let's try to look at that. It's down here. As you see, my nose is actually in the average, but if I move out, I have this what do you call that, rubber something to take something out. You can see that this is actually very nice. You can see I also have a glove right next to it, which is brown, and you can see my hand, like that. Okay, it has a red. It has a red spot on it, like this. And then if I take this, it's gonna go after this one. So it's pink tracking. Cool. Next filter. The next filters are mostly about kernels, and as you see, we have a mean filter here, a mean blur 3x3, where you see it's a bit blurry, and over here it's a bit more blurry because we use disk 7.7, and then over here we use a Gaussian, which is also blurry. That's a small difference. But let's have a look at the most interesting about the kernels are probably, of these three kernels, is probably the disk, because it's like different from the other ones, where you have a lot of values over here, and they they turn into a bell. So it's top here, moving out, moving out, moving out. Then we put all the kernels inside a kernel Gaussian two-dimensional thing going on here, and then we need to add it to our and then we divide it by, because we want to time the pixels. This is pixels we have to apply on the picture, like it's a kernel of 7.7, and we want to have the first picture up here to be timed by 1. This should be times by 4, and so on and so forth, and then we divide it by 736 because that's the total amount of them, and then we put it in the middle pixel, which is this one. Yeah, and let's have a look at the code. The code is right here, and what it does, I have for loop, going through the picture, going through the colors of the picture, having a sum which will contain all the information about the kernel, I think. Oh no, then we're gonna go through the kernels as well. So we actually have 5 for loops, and then the sum is gonna be equal or plus with pixel position kernel times with the kernel disk 3 point. This is 7. Yeah, and then we times adds the kernel on top of the pixels, on top of the pixel. This is that pixel, the mid pixel of the kernel, and then we times it with the kernel mid pixel, which we found up top. And then we put output mean disk to equal to sum, and then we get like a mean blur. Oh, yeah. Let's proceed. The next 2 pictures with kernels are Sobel and Previd, and what we do here, we have different kernels to apply to it, and then also we put a Gaussian blur on this one, the Sobel, and a mean blur on this one, Previd. But let's have a look. First, we have 2 kernels which we put on top of it. We have one horizontal, which have values up here. This is Sobel values up here. This is a Sobel because it has like goes up and down, and then it's used to edge detection. You can use it for that. And then we also do it like vertically. And then that's the first. The next part is that we take them, put them equal to sum 1 and 2, and then we take the square root of the power to 2 of it's actually Pythagoras. Anyways, and put that equal to our video texture, so we get that fine picture we just saw. And then we use the output Gaussian on one of them, so it's more blurry, it's more like nice to watch it, and not so how do you say that? Not that neat. For the glamour picture, as you see here, glamour, it's a bit more shiny, a bit more, look a bit better on this picture, we think. The way we do it is that we use the HSB again, and then we just saturate it a bit, and then we also what do we also do? We also take we just saturate it, and afterward we take the alpha of a output glamour glow solid. Oh, we take that one and put it like alpha onto it, so not too much saturation. It's like the real picture put together with the saturated picture, and it gives like a nice, what do you call that? A nice glowing effect. And then that was that it? That was it for this window. Next window. The filters we now will be looking at is the filters min, median, and max. And I should say, just like before, like the mean just took the average. Oh yeah, I did that. Oh yeah, but I didn't show it. I just want to show the mean filter, the mean kernel. It's like this one, the small one, where you just divide it by 9 each time here. Okay, but let's take a look at the other kernels. What we simply do inside these filters is that we take a kernel, I think we take 3 times 3. It's not actually a kernel, we just make a loop that runs like a kernel to see to take the 9 pixels in a kernel and put them into an array, and then sort them inside this array. So we have the smallest one first and the biggest one last. So we make a bubble sort in here. And the way we do it is that we make this bubble sort. We do it for each pixel, with all the colors. We make an eye, which controls when we have taken all the pixels. 9 pixels, I think. Let me just see. We take the kernel. We're gonna go through the kernel, and then the kernel collect the values. Let's collect the values from each inside this array, because then we're gonna change it in the array. And when the array, and then we need to have it for 0, but we need to have if I is equal to 9, because we're gonna plus it each time. So it's when it's 9, it's gonna go down here, and it's gonna loop 9 times, and loop another 9 times minus I, in order to effectivize the whole bubble sort, because we don't want to sort something that's already sorted. And then we run this. We'll take a value and the value before that in the array, and then see, if you're smaller than me, then let's why don't I take a temporary place, and you take my place? Oh yeah, and then the temporary place can go into that spot, since I'm in the temporary spot, and then they switch position, and that's basically what we do. And then they bubble sorted, so they sorted from smallest to biggest. And then what we do is that we take the output median and put it equal. We take the pixel and put it equal to that to a value inside the bubble sort. And number 4 is therefore the median, the mid kernel, the mid of the array. And then the minimum is 0 and the max is 8. And then we have this one. We take this is the minimum, so it's a bit darker, and median is it's the same, just a little blurry, I guess. And then max is where we take the light colors. They win. Yeah, that's basically how you do that. Let's take the next filter. The next filters are the emboss and the edge detection. The emboss are often used for grayscale images, or grayscale mapping, no, bump mapping. That's what it's called. But I actually didn't use. I actually used colors, but it looked a bit cool with no colors actually. So, but in order to make emboss, you use this kernel, where you take. No, sorry, that's a prereq. You take this kernel, yeah, where these 3 up here are minus and these 3 are plus. So it's like diagonal pyramid. You call it that. And then you do like all the other kernels. You simply put it inside, times it with the pixels again, like we did with the other kernels. And then you just plus with 128, since we don't want any minus numbers, some numbers less than 0. And yeah, and then you actually get the output emboss, and it looks like we just saw it. And then later on we have the edge detection, and for the edge detection we need to use a black and white binary picture, and then times it with the kernel. And the kernel edge detection looks like, and we only have the vertical axis. It looks like, let me just find it because it's just here, edge detection. It looks like this. It's kind of Gaussian. No, not Gaussian, because yeah, it meets. You can say it's kind of Gaussian, but it's more like edge detection. Where I have these are a lot different from the middle. Those are to the sides. And yeah, that's why we don't get like an edge detection around here. You can see the head, and over here you can see that it looks like a bump map. And that's basically it for that. Let's go to the next. These are the last 4 filters. The first one is the resize, the next one is the pixelate, we have the crop over here, and we have the pointed sizing. Let's just first take crop. I can just quickly explain how we did it, maybe not the right way, we don't know. But we just set the for loop to 0 or maybe alpha, in order to just show this little part of the picture. That is actually cropping. So, and over pixelate, we use a kernel. And we use the kernel where we take. Yeah, let's just look at that code. Let's see. It looks really nice. What we simply do in pixelate, we simply take the kernel and put it as our first thing we want to initiate. So first we take the top left kernel pixel and put it equal to the pixel color of the actual pixel in the mid kernel. So all the kernel pixels becomes the color of the mid pixel, and then we just make a giant jump. So we jump over, so we don't change any of these kernel pixels, and that's basically it. The way we resize is that we just take a for loop going through the loops, and then we just jump also like plus equal to. So then we also jump through the loops, but we still have some kernels that counts in the loop, counts in the whole picture. And then we simply just instead of jumping over here, it jumps, the pixel jumps. So this one jumps 3 time or 2 or something, but the actual output is shown, and this is stored in a temporary one, and temporary then assigned to the actual output resize, which only prints out or only puts it works with these x and y's instead, x2 and xy, which only whenever these jumps 2 or 4 or whatever, they just jump 1 as a normal picture, but with a different pixel value. And then we resize in that way. And that's basically it for. Then we have pointer size, our little lovely one. The pointer size, we simply go in and take output pointer size point, which is equal, and then we also have we take from the kernel. We take it from the kernel and then we jump some big jumps. Oh, sorry, we just do the same as we do in pixelate up here, where we jump bigger jumps in order to get like values like pixelate, and then we just need to make round spots instead of square frames. So we actually take this and put it equal to pixel. Our pixels would be this, and then we just can simply draw it down here. Down here we draw it, we say offset color. The color is the color of the pixel value, and then is the red, green, blue, and then we simply draw offset color. Oh, and then we of course draw it like first we draw one color and one circle and one color, and then we jump and draw the next one, some pixels later on. And then when you see them, you can actually see that each of these circles has one color, but it still looks like me. That's pointerize. And that's basically it. So let's just go through all the filters, see if we have 45, which we should have. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37 with the squares, 38, 39, 40, 41, 42, 43, 44, 45. Okay, maybe I didn't count it. It is 45 filters, and they are all really nice. Thanks for watching. I hope I pass. Yeah, I hope I pass.